Scientists have been building particle accelerators since the late 1920s. As well as letting us look at the structure of matter, they allow us to create hitherto unseen particles that our theories tell us should exist, like the elusive gluon. The secret to creating new particles lies in the most famous equation in science, E equals mc squared. What this equation means is that mass and energy are interchangeable. Particle accelerators make use of this. They speed particles up and smash them together. The energy from the collision can turn into new particles. It was in 1979, when particle physicist still wore flares, that a brand new particle detector called Petra revealed the first spectacular evidence for a force-carrying particle besides the photon. The detector produced results like this, which could only be explained by the particle that carries the strong force, the gluon. The W and Z particles took rather longer to find. That's because they were predicted to be extremely massive, and we know from Einstein's E equals mc squared that it takes a lot of energy to make a lot of mass. So it took the biggest particle accelerator of its day, the SPS, and the most sophisticated detector of its time, this UA1, to coax them out into the open. But eventually they were found, force-carrying particles like the photon and the gluon, but with more mass than a nucleus of copper. The discovery of the W and Z particles was a triumph for particle physicists, because they now had a complete set of the force-carrying particles. But that's a long way from the end of the story. Why are the W and Z particles so massive when the photon and gluon are massless? The maths just doesn't add up as elegantly as we'd like, and we suspect there's a missing piece of the puzzle. In the early 60s, British physicist Peter Higgs came up with a way of generating masses for the particles that quite magically avoided the mathematical difficulties. Now, the Higgs mechanism is quite a complicated bit of physics, but we've had over 40 years to come up with good analogies, and here's one of the best. These are physics students. They represent the Higgs particles, filling every corner of the universe. If a popular lecturer like Fred walks through the students, they crowd around to ask profound and intelligent questions, and his path across the grass is slowed down. He has acquired mass. But if a less popular lecturer walks across the grass, then everyone ignores me. I'm a massless particle like a photon, and I can travel through the universe unimpeded at the speed of light.